On May 30th, 2026, 3.5 weeks ago, CATL's chief scientist Wu Kai spoke at the 2026 Equipment Powerhouse Forum in China and made a statement that had been anticipated by the battery industry for several years. He confirmed that the manufacturing bottlenecks that had prevented sodium-ion batteries from moving from laboratory chemistry to commercial production lines had been resolved. Not that they were being resolved, that they had been resolved. CATL plans to deploy sodium-ion batteries at mass production scale in passenger electric vehicles by the end of 2026. The company has already secured what is described as the largest single sodium-ion battery supply contract ever reported globally at 60 gigawatt hours. CATL holds 37.9% of the global electric vehicle battery market, according to S&E Research, which is more than double its closest rival and more than the rest of the top 5 combined. It supplies batteries to Tesla, BMW, Volkswagen, and Ford. When CATL's chief scientist confirms that the manufacturing bottlenecks for a new battery chemistry have been resolved and that mass production is beginning, the global automotive and energy storage industries are not hearing an aspirational announcement from a small startup. They are hearing from the company that builds more batteries than anyone else on Earth, about cells made not from lithium, cobalt, or nickel, but from sodium, the element dissolved in ocean water and sitting in the salt shaker on every kitchen table in the world. MIT Technology Review named sodium-ion batteries one of its 10 breakthrough technologies of 2026. The cells can retain 90% of their capacity at negative 40 degrees Celsius, a performance level that lithium iron phosphate batteries cannot approach. Their expected price is 30% below LFP at commercial scale. CATL's next-generation sodium-ion battery has already demonstrated 500 kilometers of pure electric range in passenger vehicle testing, and Tesla has announced no commercial sodium-ion program in response. This video is going to explain exactly what CATL has built, exactly how difficult building it actually was, why the strategic implications of the sodium-ion breakthrough extend far beyond any individual vehicle range or price specification, and why the specific competitive situation for every non-Chinese battery manufacturer right now has a specific and unfavorable structure that the title of this video describes with accuracy. Subscribe right now because the sodium-ion battery story is not just an energy technology story. It is the supply chain sovereignty story that makes everything else in the technology competition between China and the West more visible. Sodium-ion batteries work on the same fundamental principle as lithium-ion batteries. Both store and release energy by shuttling ions between two electrodes through an electrolyte. In a lithium-ion cell, lithium ions move from the negative anode to the positive cathode when the battery discharges, releasing energy, and move back from cathode to anode when the battery charges. In a sodium-ion cell, sodium ions perform the same role. The physics is similar. The chemistry is different in ways that have profound consequences for both performance and manufacturing. Sodium is in the same chemical family as lithium, group 1 of the periodic table, but sodium atoms are significantly larger. The larger ionic radius of sodium means it requires different electrode materials than lithium. The graphite that serves as the anode in most lithium-ion batteries cannot efficiently accommodate sodium ions because the sodium atoms are too large to intercalate between graphite layers in the same way lithium atoms do. CATL's solution, shared broadly with the research community, is hard carbon, an amorphous form of carbon whose disordered structure has spaces that can accommodate sodium ions. Hard carbon is abundant and inexpensive. It is also significantly more difficult to manufacture to the consistency required for commercial battery production than graphite, which is why the manufacturing challenge has been harder than the chemistry challenge. The cathode chemistry for sodium-ion batteries uses materials based on sodium, manganese, iron, and in some formulations, copper and nickel, but critically does not use cobalt or high concentrations of nickel in the same way that NMC lithium batteries do. The electrolyte is sodium salt dissolved in organic solvent rather than lithium salt, using sodium hexafluorophosphate or sodium perchlorate or similar compounds. The overall material system is less dependent on rare or geographically concentrated materials than any of the dominant lithium battery chemistries. Lithium is not a rare element by absolute abundance, but it is concentrated in the lithium triangle of Argentina, Bolivia, and Chile, in the salt flats of the Atacama Desert, and in specific Australian hard rock deposits, with refining concentrated in China. Cobalt is critically concentrated in the Democratic Republic of Congo. Nickel has its own supply chain geography. Sodium is the 6th most abundant element in the Earth's crust and is dissolved in every ocean on the planet. The supply chain advantage of using sodium instead of lithium is not that sodium batteries are cheaper to manufacture today, though they are approaching cost parity. It is that the upstream raw material supply for sodium batteries is effectively unlimited and globally distributed in a way that creates no single point of leverage for any country or consortium. Subscribe and hit the like button right now, because the specific manufacturing challenges that prevented this chemistry from reaching commercial production for years, and the specific ways CATL solved them, are the story that most consumer coverage of sodium batteries has treated as a footnote to the headline, and that actually explains why this announcement is a genuine breakthrough rather than another battery technology promise. CATL's CTO Gao Huan disclosed at an industry event in April 2026 that the company had overcome 4 major manufacturing hurdles that had blocked commercial production of sodium-ion batteries, despite the chemistry being well understood in principle. The first hurdle was extreme moisture control. Hard carbon anodes are far more sensitive to moisture than graphite anodes. A lithium-ion factory requires controlled humidity to prevent moisture damage to the lithium salt electrolyte and the electrode materials. A sodium-ion factory using hard carbon anodes requires moisture control at a more stringent level, because the hard carbon absorbs ambient moisture during manufacturing in ways that degrade capacity and cycle life if not controlled to tighter tolerances. Achieving the manufacturing environment and process discipline required for commercial-scale hard carbon electrode production required CATL to develop new dry room technologies and process controls beyond those already in place in its lithium-ion facilities. The second hurdle was hard carbon gas generation. During the formation cycling process that activates a battery cell after assembly, hard carbon anodes generate gas bubbles that, if not managed, create pressure that deforms the cell and degrades performance and safety. Controlling this gassing requires precise management of formation protocols and electrolyte formulation in ways that took CATL significant development time to master at commercial scale. The third hurdle was aluminum foil bonding. Lithium-ion batteries use copper foil as the current collector for the anode because lithium does not alloy with copper, and because copper's electrical conductivity and mechanical properties are suitable. Sodium, however, does alloy with copper at certain potentials, so sodium-ion batteries use aluminum foil for the anode current collector instead. Aluminum is cheaper than copper, which is one of the cost advantages of sodium batteries, but aluminum foil creates bonding challenges with the active electrode materials that required specific process development for reliable adhesion at the coating speeds needed for commercial production. The fourth hurdle was mass production of self-generating anodes, a category of hard carbon electrode design that offers performance advantages but requires manufacturing processes that had not previously been executed at gigawatt-hour scale. CATL's CTO stated that the company had systemically addressed over 100 engineering challenges to enable commercial-scale production of sodium-ion batteries. 100 engineering challenges, solved one by one over 4 years of development investment, enabled by 10 billion yuan of R&D spending, and the manufacturing expertise that comes from producing more batteries than any other company on Earth. The word breakthrough in the headline of this video deserves its place, not because the chemistry was discovered in the last year, but because the manufacturing capability that makes the chemistry commercially relevant was confirmed as solved on May 30th, 2026. The performance specifications that CATL has confirmed for its Naxtra sodium-ion battery product line establish what the commercial product actually delivers compared to the lithium alternatives it will compete with. The most important specification for EV applications is energy density. CATL's second-generation sodium-ion cells exceeded 200 watt-hours per kilogram, up from 160 watt-hours per kilogram in the first generation. The comparison point is lithium iron phosphate, the dominant chemistry for budget and mid-range EVs in China and increasingly globally, which typically delivers between 150 and 180 watt-hours per kilogram in commercial cells. CATL's sodium-ion cell exceeds the bottom of the LFP energy density range and approaches the middle of it. It does not yet match high-energy NMC lithium cells at 250 to 300 watt-hours per kilogram. For the applications where CATL is initially deploying sodium-ion batteries, including light commercial vehicles, electric scooters and motorcycles, battery swap infrastructure, and lower-priced passenger EVs, the 200-plus watt-hour per kilogram energy density is sufficient to deliver useful range, with 500 kilometers cited by CATL as the next-generation target for passenger vehicles. The temperature performance is where sodium-ion most clearly outperforms lithium iron phosphate. LFP batteries deliver significantly reduced range in cold weather because the lithium-ion chemistry slows substantially at low temperatures, a practical problem for EV owners in northern Europe, northern China, Canada, and the northern United States, where winter temperatures fall well below 0 Celsius. CATL's sodium-ion cells retain 90% of their nominal capacity at negative 40 degrees Celsius. No lithium battery chemistry approaches this level of cold weather performance. The safety profile of sodium-ion batteries is superior to all lithium chemistries in the specific failure mode of thermal runaway. the condition where a battery cell overheats and releases heat that causes adjacent cells to overheat in a cascade that can produce fire or explosion. Sodium-ion cells, because they do not contain lithium, cobalt oxide, or high nickel cathode materials, have significantly lower thermal runaway risk than NMC lithium batteries, and somewhat lower than LFP batteries. The expected cost at commercial scale is approximately 30% below LFP, which is itself the cheaper of the dominant lithium battery types. CATL installed 29.06 gigawatt hours of EV batteries in China in April 2026 alone, holding 46.6% of the Chinese EV battery market in that month. When the world's largest battery company by volume begins deploying a new battery chemistry at commercial scale, the cost reduction that scale enables will arrive faster than it would for any other battery manufacturer. The 60 gigawatt-hour sodium-ion supply contract that CATL has secured, described as the largest single sodium-ion supply contract ever reported, is the commercial signal that most clearly indicates the sodium-ion transition is not a laboratory achievement or a future aspiration. A 60 gigawatt-hour contract at expected sodium-ion cell pricing represents a supply commitment worth billions of dollars, and an installation rate that would support a significant fraction of the annual battery demand for a mid-sized automotive program. The identity of the counterparty to this contract has not been publicly confirmed, but the scale of the commitment suggests a major automotive manufacturer or grid energy storage operator with confidence in CATL's delivery capability and in the technology's readiness for commercial deployment. The 60 gigawatt-hour contract arriving simultaneously with WuKai's May 30th manufacturing confirmation and the planned second half 2026 passenger EV rollout creates the commercial conditions for sodium-ion batteries to become visible in the market during the second half of 2026, rather than remaining in the prototype and pilot phase that has characterized previous announcements. The CATL Naxtra product line spans passenger EVs and commercial transport. A 24-volt integrated truck battery tailored for heavy-duty logistics has been confirmed as a product. Passenger models can hit over 500 kilometers of range, with full climate adaptability across the temperature range. CATL estimates next-generation versions could supply nearly half of China's passenger vehicle demand by 2026, a projection that reflects the combination of CATL's manufacturing scale and the cost and performance profile of sodium-ion relative to LFP, MIT technology. Review's designation of sodium-ion batteries as one of the 10 breakthrough technologies of 2026 provides the most credible independent validation of the technology's significance. MIT Technology Review's annual Breakthrough Technology List is not a marketing document. It is an assessment by the editors and writers of the most rigorous technology journalism publication in the United States, selecting 10 technologies that represent genuine scientific advances with meaningful near-term commercial and social impact. Sodium-ion batteries appeared on that list because the combination of CATL's manufacturing breakthrough and the technology's performance and supply chain advantages makes this the year when sodium-ion moves from laboratory chemistry to commercial infrastructure. The strategic significance of sodium-ion batteries is not primarily about the specific range or price of any particular cell. It is about what this technology shift does to the global battery supply chain and to the competitive positions of the non-Chinese companies that have been trying to challenge China's dominance of battery manufacturing. The battery supply chain for lithium-ion batteries depends on lithium from the Lithium Triangle and from Australia, cobalt from the Democratic Republic of Congo, nickel from Indonesia and the Philippines and Russia, and manganese, graphite, and rare cathode precursor materials from geographically concentrated sources. China has spent 2 decades building the refining capacity, the chemical processing expertise, and the manufacturing knowledge to dominate the conversion of these raw materials into battery cells. Western companies that want to compete in lithium battery manufacturing, including Northvolt in Sweden, Panasonic in Japan and Kansas, and LG Energy Solution and SK Innovation in South Korea and the United States, all have to access the same raw material and precursor supply chains that China has built its advantage around. Northvolt burned through $10 billion in investment and filed for bankruptcy without achieving the manufacturing scale and yield rates needed to compete with CATL's cost structure. The bankruptcy of Europe's most serious battery manufacturing challenger, at the very moment CATL is launching a new battery chemistry, illustrates the competitive gap between Chinese battery manufacturing capability and Western battery manufacturing capability in concrete and consequential terms. Sodium-ion batteries do not change the competitive gap, they extend it. CATL has solved the manufacturing problems of sodium-ion batteries. Any company that wants to compete in sodium-ion manufacturing needs to solve the same 100 engineering challenges that CATL has spent 4 years and 10 billion yuan solving. The manufacturing knowledge that solves those challenges is not published in academic papers in sufficient detail to replicate. It is embedded in CATL's process controls, its equipment specifications, its operator expertise, and its production management systems. The competitive moat that sodium-ion creates for CATL is not primarily about the chemistry, which is in principle publicly available. It is about the manufacturing knowledge that translates the chemistry into reliable commercial cells at competitive cost, which is accumulated rather than discovered, and which CATL has accumulated faster and more thoroughly than any competitor. The Tesla dimension of this story, the part that the title addresses specifically, is about competitive positioning rather than about any specific technical failure on Tesla's part. Tesla does not make its own battery cells in significant volume. It uses cells from CATL, from Panasonic, and from LG Energy Solution, and it operates its own 4680 cell manufacturing at Gigafactory Texas in increasing quantities. Tesla's 4680 cell is a cylindrical lithium cell using a variant of NMC chemistry for the cathode and silicon carbon composite for the anode, designed for higher energy density and faster manufacturing than previous cylindrical cell formats. Tesla has not announced a sodium-ion battery program of any commercial significance. The 4680 development, which has been the center of Tesla's battery strategy for the past 5 years, is a lithium technology. It competes in the premium energy density segment where sodium-ion's current energy density is insufficient, but it does not address the segment where sodium-ion's advantages, cost, cold weather performance, and supply chain simplicity are most compelling. If CATL's sodium-ion cells capture 30 to 50% of the LFP market in China by 2028 or 2029, as the company's projections suggest, the cost structure of Chinese EVs using CATL sodium-ion batteries will be lower than the cost structure of equivalent vehicles using lithium batteries of any chemistry. Tesla competes in the global EV market. Its Chinese competitors, which include BYD, NIO, Li Auto, Xpeng, and Chery, will have access to CATL's sodium-ion cells on the same terms as any other Chinese automaker. Tesla will not have equivalent cost access to sodium-ion batteries at commercial scale because CATL's supply agreements with Tesla are for lithium cells. The question of when Tesla would seek a sodium-ion supply agreement with CATL or develop its own sodium-ion capability is a question about strategic timing that Tesla has not answered publicly. What is publicly answered is that as of June 2026, Tesla has no announced commercial sodium-ion program, and CATL's chief scientist has confirmed that mass production of sodium-ion cells for passenger EVs is beginning. The competitive gap in battery chemistry strategy, with CATL now deploying 2 parallel commercial battery chemistries and Tesla deploying 1, is the specific competitive dimension that the title of this video describes. Subscribe to this channel, like this video. Because the salt battery that China just built at commercial scale, at 30% lower cost than LFP, with 90% capacity retention at negative 40 degrees after solving over 100 manufacturing challenges, is not a future threat to lithium dominance. It is a present transition in who controls what batteries the world runs on. The DeepSeek parallel that some technology commentators have drawn between CATL's sodium-ion achievement and DeepSeek's AI efficiency breakthrough is more than a rhetorical device. The structural similarities between the two stories are genuine and illuminate something important about China's competitive approach to technology. DeepSeek achieved competitive frontier AI performance using dramatically less compute than U.S. competitors by developing algorithmic efficiency innovations that compensated for hardware constraints created by chip export controls. CATL achieved commercial-scale battery manufacturing using dramatically more abundant raw materials than its lithium battery competitors by solving the engineering challenges that prevented sodium chemistry from reaching production scale. In both cases, a Chinese company operating within the constraints created by U.S. strategic competition, DeepSeek with hardware restrictions, and CATL with supply chain awareness of lithium's geopolitical concentration, developed solutions that reduce dependence on the constrained resource. DeepSeek's algorithmic efficiency is now being adopted by U.S. AI research labs, improving the performance of competitors who did not develop the innovations themselves. CATL's sodium-ion manufacturing knowledge creates a competitive moat precisely because it cannot be similarly adopted by competitors who did not do the work. The difference between the two parallels is the one that matters. Open source software spreads algorithms globally. Proprietary manufacturing processes stay within the companies that develop them. CATL's sodium-ion advantage is not transferable in the way that DeepSeek's published research is. This makes the structural competitive position CATL occupies in sodium-ion batteries more durable than the algorithmic advantage DeepSeek achieved in AI, because the latter was open-sourced, while the former is embodied in manufacturing capability that is not. Subscribe. The CATL sodium-ion story is the battery story of 2026, and this channel will follow every milestone in its commercial deployment as it arrives. The grid energy storage dimension of sodium-ion's commercial rollout deserves specific attention because it extends the significance of CATL's manufacturing breakthrough well beyond the automotive application that has received the most media coverage. Battery storage for electrical grids is one of the fastest growing markets in the energy transition, driven by the expansion of solar and wind generation, whose intermittency creates demand for storage that can absorb excess generation and release it during periods of low generation. Grid storage batteries do not face the same weight and volume constraints that EV batteries face. A grid storage system does not have to fit inside a vehicle's wheel wells or fit within a vehicle's weight budget. This relaxes the energy density requirement that has been the primary limitation of sodium-ion batteries relative to high-energy lithium alternatives. For grid storage, where the battery sits on a concrete pad and size and weight are secondary to cost, cycle life, and safety, sodium-ion's advantages are most compelling and its disadvantages least relevant. CATL's December 2025 announcement of large-scale sodium-ion deployment across 4 sectors in 2026, which explicitly included energy storage alongside battery swap systems and passenger vehicles, reflects the company's recognition that grid storage is the highest volume and most immediately attractive commercial application for the sodium-ion chemistry. Interconnecting renewable energy generation with battery storage using sodium-ion batteries would create a supply chain that does not depend on lithium from the Atacama Desert, cobalt from the Congo, or nickel from Indonesia. The strategic implications of a renewable energy grid storage market that is largely independent of the specific raw materials that have been the focus of critical mineral strategy in the US and EU are substantial. The US has spent significant political and financial capital on securing lithium supply chains from Australia and South America, and on developing domestic lithium mining and refining capacity through the Inflation Reduction Act's battery supply chain provisions. If sodium-ion batteries capture 30 to 50% of the grid storage market by 2030, as CATL's projections suggest is possible for the price-sensitive end of the market, the strategic value of the lithium supply chain investments currently being made changes substantially. Subscribe to this channel, like this video, because the sodium-ion story is not just about electric cars or about any individual technology competition. It is about the supply chain architecture of the energy transition, and about which countries and companies will have the manufacturing and raw material advantage in the energy systems of the 2030s. CATL has announced that the salt battery is ready. The history of lithium as the only viable energy storage chemistry for EVs and grid storage is being made right now. The response from Western battery manufacturers and automakers will determine whether the lithium era remains competitive or whether sodium becomes the chemistry that defines the next decade of energy storage. The specific commercial timeline for sodium-ion battery deployment that CATL has confirmed through multiple 2026 announcements creates a forward-looking calendar that is worth stating precisely because it defines the period during which the sodium-ion transition becomes visible in the market. Battery swap systems using sodium-ion cells are already being piloted in cities including Shenzhen, where stations for electric scooters and delivery vehicles are being tested. Passenger EV deployments are confirmed for the second half of 2026, with GSE Ion EVs among the first models to receive sodium-ion packs. The 60 gigawatt-hour supply contract implies delivery beginning in 2026 or early 2027. Commercial vehicles, specifically light trucks and vans, are already using CATL's 45 kilowatt-hour sodium-ion truck battery launched in early 2025. CATL's own internal target is that next-generation sodium-ion versions could supply nearly half of China's passenger vehicle demand. By 2030, if CATL's projections and MIT Technology Review's designation are both accurate, sodium-ion batteries will be a major presence in the global EV and grid storage markets. Every major Western automotive and energy storage company that has not yet secured a sodium-ion supply relationship or developed its own sodium-ion manufacturing capability will be purchasing cells from CATL or from the smaller Chinese sodium-ion battery companies developing behind CATL's market leadership. The lithium history that China's salt battery is making is the history of a technology transition that began in a laboratory, faced years of manufacturing obstacles, was solved by the world's largest battery manufacturer through sustained engineering investment, and arrived in commercial production at the moment when the EV market is large enough for the transition to matter globally. Whether the Western automotive industry, including Tesla, follows or leads this transition is the strategic question that the next 3 years will answer. Subscribe, like, share. The salt battery is real, the manufacturing challenges are solved, the commercial deployment has begun, and the history of who built the battery storage systems that power the 2030s is being written right now.